Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, and today we will continue with module 5, that is principles of texture measurement by X-ray diffraction. And today is lecture number 24, where we will try to understand characteristics X-rays, absorptions and filters for the these characteristics X-rays. So, the concepts that will be covered in this lecture will be Laue method of diffraction, Derbyshire method of diffraction, absorption and penetration depth, filters that are required to get monochromatic X-rays, effect of lattice strain on diffraction width and the positions of the peak. So, let us start. What is Laue method of diffraction? You see that when the X-rays were initially invented, and then there were continuous X-rays, and then with the further invention the monochromatic X-rays were found out. Now, the point is that during that time when the X-rays just came into existence, known to the mankind, then you see Laue used a method where he used an X-ray to diffract a single crystal, and this diffraction was done in such a way that the wavelength of the X-ray is varied, and that is why it is not monochromatic, it is a continuous X-rays, and the theta is kept constant. And in this way you see both in the reflection mode and in the transmission mode, the HKL planes, different HKL planes that could diffract at the same theta angle, because the lambda of the wavelength of the X-rays are varying, and it may at some theta will support the Bragg's law, and therefore such kind of pattern, a pattern schematic of a pattern of a single crystal, of a certain single crystal is shown here. So, you see in this manner a large number of spots that are symmetrically arranged in a characteristic pattern could be observed, and this is known as the Laue method of diffraction. Later Derbyshire modified this method of diffraction and used characteristic X-rays, that is monochromatic X-rays, to diffract different HKL planes at different Bragg's angle theta, right. So, you see here is the schematic of the construction of this kind of an experiment, where a small sample, maybe a single crystal or a powdered polycrystal, is placed at the center, and it is surrounded by the detector, a phosphor screen which is rounded down to capture the intensities observed at various Bragg angles. So, you see either it is rotation of a single crystal, and then it is called the single crystal rotation method, or it is analysis of multiple grains using random texture. How we can obtain that? By making a keeping a powdered sample with lots and lots of powdered particle having multiple grains even in a single powder. So, this is known as powder diffraction method. So, what happens if you look into the schematic? So, there is this phosphor screen, and the X-ray beams falls on the sample where the sample is being rotated, and you see that while the X-ray beam falls on the sample, various HKL planes, they will diffract at various theta angles, which is basically the angle theta defined by the Bragg's law, that is n lambda equal to 2d sin theta, right. So, you can see that various diffraction de Sitter lines or de Sitter curves could be obtained, right. If we straighten this strip, we can see that this strip will basically look something like this, where the direct X-ray beam also passes through and there is a hole, a small hole here where it passes, right. So, you see in the X-ray diffraction, absorption and penetration depth is a very important factor. It decides whether the radiation, not only the X-rays, the radiations, that is X-rays, neutrons, electrons, whether they are how much they are interacting and how deep it is going into that matter. So, because of the nature of the interaction of the X-rays, neutrons and electrons, there is a substantial difference between the absorption of the radiation of these radiations with the matter. So, you see, if a radiation of an intensity I0 is incidented on the surface of a particular polycrystalline metal, then the intensity I, if it of a certain thickness, say the thickness of that particular specimen or sample is T, and then the intensity I comes out, then the relationship between the final intensity I and the incident intensity I0 is I equal to I0 exponential minus mu T, where mu is the linear absorption coefficient and T is the thickness of the sample. Now, you see the linear absorption coefficient has an unit of per centimeter, and depending upon the type of the radiation, its wavelength and its way of interaction with the matter, this linear absorption coefficient varies, and this linear absorption coefficient can be given by mu equal to minus of differentiation of the intensity by the intensity delta x. So, delta I by delta x and by the intensity. So, this is just the different form of showing this same equation, where we can find out the linear absorption coefficient. Now, you see, usually the linear absorption coefficient is not shown in terms of mu, rather it is shown in terms of mu by rho, where mu by rho is basically the mass absorption coefficient, here it is, and is given by the unit centimeter square per gram. Now, where rho is the specific weight of the interacting material, right. Now, you see that if that interacting material is not a single polycrystalline metal, but a mixture of one or two metals, that is it's kind of an alloy, then you see then the summation of the the mass absorption coefficient mu by py and the weight fraction of that particular individual element present in that alloy is used to calculate the total mass absorption coefficient for that particular polycrystalline material, which is not a single metal, which is not made up of single element, but multiple elements, right. That is an alloy. Now, if we look into the mass absorption coefficients relationship with the wavelength. So, you see that let us take a copper radiation, let us take a copper radiation. Okay. So, this radiation, say that it is coming it's a continuous radiation coming from copper anode, and now you see that if we plot the lambda, which is in the x axis, versus the energy per unit quantum, then you will find out that as the lambda is decreasing, the energy of this radiation is increasing, because you see that the relationship of energy, that is W, is equal to h mu, right. H is the Planck's constant and mu is the frequency, and so is equal to h c by lambda. So, you see that as the energy of the incident radiation is increasing, the lambda is decreasing. Now, if you look closely, we can see that if this continuous radiation coming from copper is incidenting on, say for example, a nickel which has a little lower, an atomic number lower. Nickel has an atomic number of 28, whereas copper I think is 29. So, you see that as if we look into this curve, this is the curve which is between the x axis is lambda and the y axis is the mass absorption coefficient, that is mu by rho. And you see that as the incident X-ray radiations, energy is increasing, that is the lambda is decreasing, the mass absorption is decreased, right. So, the penetration depth is increased. But if we look at this whole curve, if we look here, there is another curve which has the same trend, that as the wavelength is decreasing from 2 to 1.5, the mass absorption coefficient is decreasing. But at a certain energy of this incident X-ray, there is a large peak, and this peak corresponding to the energy Wk is seen, and this peak is said to be the K absorption S, or the K excitation voltage, K excitation energy. So, you see, with respect to this formulation that the energy is equal to h mu is equal to h c by lambda, one can say that for this particular K absorption edge or K excitation energy, we can find out Wk, the energy for that is equal to h times mu k is equal to h c by lambda k. So, at this particular lambda, when the energy is increased and the lambda is decreasing slowly and slowly, and it is coming to this lambda, the energy becomes so high that at this critical energy, the K shell electron from the nickel could be ejected. So, an energy of such level, Wk level, when it incidents on the nickel, it is capable enough to eject a K shell electron from nickel. And when it is done, the nickel goes to a very high energy state, right. And then what happens, that when the L shell atom of the nickel goes to the K shell atom of the nickel to reduce its energy to come to the ground state, then another characteristic wave X-rays of characteristic radiation of a certain wavelength is released also from nickel. We will talk about that later. But you see that even though as the X-ray wavelength is shortened and shortened, reduced, the penetration depth reduces because the mass absorption coefficient is reducing. But at certain critical excitation energy or critical excitation voltage, what happens, that it is enough to eject a K shell electron from nickel, and this we are talking about if the radiation is from, say for example, a copper, and it is falling on nickel, and then it is able to absorb energy, so that the K shell electron is excited and goes away from the atom, and then that excited atom, that is known as the K absorption edge, right. So, you see that X-rays are absorbed by matter by this scattering and true absorption, and you see that the total absorption including scattering plus true absorption is equal to mu by rho. Now, scattering is though responsible for a small fraction of this absorption, but most of the total absorption is basically based upon the true absorption. Now, here you see we will show we are showing another schematic, and you see what we are showing here is a schematic where the lambda that we have shown up to 2.0, we are extending it to a higher lambda, and you see the x axis is basically lambda and the y is again mass absorption coefficient. So, what we mean to say here is that when the K excitation energy is incidenting, a radiation of sufficient energy which is equivalent to that critical K absorption edge or K excitation energy is incidenting on another material, say nickel in this case as an example, then the K absorption edge is always there, which shows a higher mu by rho at a certain wavelength, but also there will be the L absorptions altogether, because the L absorption that occurs because of the the critical energy that is required to eject an L shell electron, and there are 3 L levels, L1, L2 and L3 say, then there could be 3 peaks of mass absorption coefficient. So, you see that while we get a K absorption S, it will not be devoid of L absorption S, because to obtain L absorption S, the excitation energy required by the incident radiation is quite low. So, K absorption edge is always, it includes the L absorption edge also. So, it happens all together. Now, very importantly, one very important thing you see that while the wavelength is reduced for this curve, and you see that there is a high absorption coefficient here, and when the lambda is reduced, the energy W is basically increasing more and more than the Wk, right, and thereby it can always cause the K excitation, and therefore there will be always a K absorption edge, but you see that the absorption is reducing as the lambda is decreasing. The absorption is reducing as the lambda is decreasing, and therefore the penetration depth is basically increasing. Now, you see that what we are talking about regarding this true absorption. What we mean to say is that, say look into this schematic, and you see that if 0 is the position of the energy for the neutral atom, and you see that this is basically the energy for the metals which are present in a polycrystalline material, because you see that the metals in a polycrystalline metal, the atoms are are present in the sea of electron, right. So, the valence electron is basically removed from the atom and then it is there. So, it is slightly in a higher excitation state, and then you see that whenever the energy of a sufficient level, that is you see Wk is enough to eject a K shell electron, the energy say for this is this much. So, from 0 to here. So, this much energy if it is given, then it is able to eject a K shell electron, and then you see that when this energy, when the atom is in such energy state, that is the K state where the K electron is removed, and then the electron from the L shell goes to the K shell, right, and is shown like this. So, there is a reduction of energy from Wk to Wl, or the electron from the M shell goes to the K shell, that is the reduction of energy from here to here, right. So, this is the, you see this is the N state, N electron removed, M state, the M electron removed, the L state, the L electron removed. So, if we look into this schematic properly, we can say that in order to remove the K shell electron, we need an energy Wk. In order to remove the L shell, we need an energy Wl. To remove M shell, we need just Wm, and then Wn for the N shell. Now, the point is that you see that when the Wk is given, the K shell electron is removed, and the probability that M shell atoms M shell electron will fill the K shell is lower than the probability that the L shell electron will fill the K shell. Therefore, the K alpha is usually have a very high intensity as compared to the K beta, and so K beta is from electron from M to K, and K alpha is the electron from L to K, right. Now, you see L has 3 subshells, and that is L1, L2 and L3, and it is shown here. And you see when K falls from K to L3, it is K alpha 1, and when it falls to K L2, it falls from L2, it is K alpha 2, right. Now, what happens here is that when these as I said, that electrons from L produces K alpha, electrons from M produces K beta, and these are the characteristics wavelength, and this wavelength will have a characteristic particular wavelength, a particular wavelength. So, you see that when Wk is given, Wk is the excitation energy, which is equal to h mu k, which is equal to hc by lambda k. So, this particular critical excitation energy or critical excitation lambda k, lower lambda k as we are lowering it, it allows the electron from the K shell to be removed, so that let us say electron from the L3 is reaching the K shell, and then it is emitting a characteristic radiation. And this characteristic radiation, as I was saying in the last slide also, this characteristic radiation, say it has a frequency mu k alpha 1 or 1 by lambda k alpha 1, means basically lambda k alpha 1 is its wavelength, right. So, using this equation, you see the energy of that radiation is h times mu k alpha 1, and then this is basically the energy corresponds to this Ka, and this Ka is basically corresponding to Wk minus WL3, right. So, Wk minus WL3 is equal to h mu k from this minus h mu L3, right. So, if we get a relationship between the X-rays emitted from that particular element which is radiated, say copper X-ray is used to radiate nickel, as I said earlier, and then the radiated wavelength of this characteristic radiation has a wavelength of lambda k alpha 1, right, and which is equal to 1 by lambda k minus 1 by lambda 3. So, this is basically the absorption edge or the emission line wavelength, right. So, lambda k and lambda 3 is the K and the L3 excitation or absorption edge. So, thus this is by the way the absorption in a metal takes place, absorption of X-rays. So, if we look into this energy, that is Wk, the K excitation energy, this is equal to, you see, the in terms of electron volt EV, right. So, the critical excitation energy, which is equal to h mu k, that is equal to hc by lambda k, is the energy of the X-ray beam which is generated because of the in the X-ray tube the electrons from the cathode hits the anode, and in this case the anode is the copper anode, right. And as the energy of this electrons are increasing, the voltage, means we have to increase the voltage to increase the energy of the electron, so that the electrons that is hitting the anode can produce more and more intensified X-rays. So, Wk is related to electron volt, right. Electron into voltage is the energy of the electron beam, which is converted into copper K alpha radiation and the other continuous radiation. So, as the Wk is basically related to Vk. So, if we find out the voltage of that in the of the X-ray tube, Vk is equal to Hc by E, which is the electronic charge, lambda k, right. So, Vk is equal to H, which is 6.626 into 10 to the power minus 34 Planck's constant. C is the speed of the light, 2.998 into 10 to the power minus 34, divided by the charge of the electron, which is 1.602 into 10 to the power minus 19 times lambda k. It comes up to be 1.24 into 10 to the power 4 by lambda k. So, the voltage required to produce a certain K excitation wavelength can be calculated by this method. So, this method of mass absorption of X-ray radiation can be used to filter the continuous X-ray to obtain monochromatic radiation, because monochromatic radiation can be used for diffraction experiments to obtain information in a much more detailed manner. So, you see that if a X-ray tube is operating at certain voltage Vk and it is producing K alpha and K beta radiation, and it is also producing definitely the continuous spectrum, but as I said earlier in the earlier classes, that as the voltage of the X-ray tube containing cathode and anode is increased, the electrons from the cathode reaches the anode, and the intensity of the continuous radiation keeps on increasing as the voltage is increased, right. And at certain voltage, K alpha and K beta radiation starts to form, and as the voltage of that X-ray tube is increasing, the lambda SWL, that is short wavelength limit, is also decreasing. The intensity of K alpha and K beta is also keeping on increasing, but it is important to know that to do diffraction experiments, only a single monochromatic radiation, that is K alpha, is required, which has the highest intensity, whereas the K beta has to be removed. Now, if the beam containing this K alpha, K beta and other continuous radiation is passed through a filter, the filter is a metal which should have a K absorption edge which lies between the K alpha and K beta. Then it can absorb the K beta line and excites its K shell, means the K beta line, that this radiation can give enough energy to that filter metal, so that its K electron is ejected out, and if any electron from the L or M shell is falling on this K shell atom of this filter metal, then that characteristic radiation is dispersed everywhere, and it will not go to the detector. So, it will absorb the K beta as well as a part of continuous radiation, and therefore, you see, if copper X-ray tube is used to produce the K alpha of copper, then the nickel, which has an atomic number lower than copper, can be used to filter out the K beta, and this helps the material to this helps us to obtain characteristic K alpha radiation. Now, the intensity of K alpha to K beta is of the range of 500:1 after the filtration takes place, and so it reduces, and before the filtration it is in a range of 9:1. And you see that nickel, which is used as a filter, has an atomic number of 28, one lower than the copper, which has an atomic number of 29. So, using this technique one can obtain, you see, characteristics copper alpha radiation, and this copper alpha radiation of characteristics lambda equal to 1.54 can be used to obtain diffraction pattern from various metals and alloys. And you see, here is an example of the diffraction pattern obtained from this kind of copper alpha radiation, and this you can see that we have obtained a peak at 110, another peak at 200, another at 211, 220, 210, and this peaks shows that this is a BCC material, and thus this shows the importance of characteristics radiations. Now, you see that whenever we are doing diffraction and at a particular theta a peak is coming, and that theta, basically that theta angle, the Bragg's angle theta, is basically representation of that particular HKL plane, right. So, you see, when the metal has no strain at all and it's in the nascent state, and then that the d, that is the interlamellar distance between the plane d, is equal to what it should have, it should come for that particular theta, right. So, n lambda equal to 2d sin theta. So, this d and theta is basically known that, okay, for a particular material, and if the I am going to the previous slide, and if the material is diffracting from a certain HKL plane, say 110 plane, the interplanar spacing between this is already known. So, the theta is already decided, right, and this is decided for 110, for 200 and 211, and it is fixed at certain theta. But you see that when the material is under some kind of a stressed condition, say if there is a uniform stress in such a way that this d, the interlamellar spacing for that particular plane, is increased, then what happens, that n lambda equal to 2d sin theta equation, if we use, that is the Bragg's law, when you use it, we will find out that theta, that is sin theta, becomes equal to n lambda by 2d, right. So, as d is increasing, the theta has to decrease. So, you see that when there is no strain, the intensity of the theta is obtained at the exact theta peak as per the Bragg's law for that particular HKL plane. But if it is under uniform strain, that is, if d is higher, then the theta basically decreases, and if the the peak shifts towards the lower 2 theta value, right. So, as if it is strained in such a way that the d is the interlamellar spacing is decreased, then the theta basically increases. So, the peak shifts at a higher 2 theta. This peak shift, as I said, depends upon as the Bragg's law has to be followed, and the d spacing alters when there is a uniform strain. So, there is a peak shift either below that particular Bragg's angle theta b for that particular HKL plane, or increases depending upon whether the uniform strain is stretching the distance between the plane or it is compacting it. And in case of non-uniform strain, the strain is such a way that the HKL plane in one position they are compressed, and so the d is reduced, and in other place it is basically the d is increased. So, if we look into this figure, we see that the d is basically a variable, right. So, d1 at the bottom is less than the d1 at the top, and it is basically in the bottom is less than the actual D0 without strain. So, what happens that for the where the D is increased, that is in the top, the peak shift occurs towards the negative direction, towards the lower side, and you see what happens that the peak is shifting this side then, right, and when the D is decreased in the bottom, the peak is shifting towards this side, right. Let me start with the laser pointer. So, when the D is decreased, the peak shifts towards this direction, and if the D is increased, then the peak shifts towards this direction, and leading to thickening of this peak, and it becomes something like that. So, it is also important to understand that how de-spacing and the changes in the de-spacing may occur in the material under some kind of processing conditions, which leads to change or shifts in the peak, or increase the the volume of the peak, spreading of the peak that may occur. So, what we understood from this today's lecture, we understood that there are methods which is called the Laue method of diffraction, where the experiment is done in such a way, a continuous X-ray with variable wavelength is taken, and the theta is kept constant to obtain diffraction from various HKL planes. On the other hand, with the advent of characteristic radiations and with the increase in the use of the filters like nickel filter for copper, we can use Derbyshire method of diffraction, where lambda can be kept constant. That means carectaristic wavelength K alpha radiation can be obtained, and the theta is varied to obtain various HKL diffraction information from various metals and alloys. Now, importantly, what you observe that K excitation or absorption edge is the increase in the absorption of X-ray by a metal at a certain fixed lambda, that is some critical lambda, excitation edge lambda, whatever you say, where the energy of the X-ray is increased and the lambda is decreased to a certain critical value, so that it becomes sufficient to eject a K shell electron from another metal, from the metal, and this mechanism can be used to make filter material to filter out K beta radiation from and some continuous radiation from the K alpha radiation, so that a higher intensity of K alpha radiation could be obtained. So, a filter material is used is actually a 1 atomic number less than the target metal, so that it can absorb the K beta line. So, in case of copper, nickel is used as a filter. So, as the metal with 1 atomic number less has a K absorption edge in between the K alpha and K beta of the target metal. Thank you. That's okay. One more thing, lattice strain affects diffraction width and peak position. We have seen that. Thank you very much.